The Science and Cosmetology department? That should be Cosmology. Why do you always get those two confused? I always think the one about space should have an ET in it. Kind of makes sense to me. We're going to continue on our work with cosmology with evidence and support of BBN, Big Bang nucleosynthesis. Starting off with the premise of cosmic background radiation, CBR, or cosmic microwave background radiation, CMB, and sometimes relic radiation. So to help us think about what CBR is, I want to refresh our memory of, here's looking at HuKit, page 18, particularly the portion of the color spectrum that we are able to detect with our eyes, the colors from red to blues. Yes, there's violet, but we stick to reds and blues as the extreme in astronomy. And the energy levels, red being the lower energy and the blues being the highest energy. Now, at the time of the Big Bang nucleosynthesis singularity expansion of space, we have knowledge that this had to take and require an enormous amount of temperature. And there's a formula with the Hubble-Lemaitre law that the inverse of gives you a value for the age of the universe, usually about 13.5 billion years. So what we're able to do is recognize that if this is the likely very high temperature of the universe, and everything existed at that point in that singularity and expanded at the same rate, we can then do the math to recognize that the universe has cooled down by a constant rate through time. And the scientists have determined that this temperature, those photons, those energies, would have cooled down from very high energy of gamma rays, should now, 13.5 billion years later, cool down to about the microwave range. If we think of it as a timeline, the expansion of the Big Bang nucleosynthesis singularity, this cosmic microwave background radiation is like the earliest scattering of light. And dark age, just referring to as more of the photon nuclei were forming, collisions occurring to get us galaxies, clusters, and things that are in our universe. So this cosmic microwave background radiation, if you go farthest back into the universe, as you can detect, the photons of the earliest time origin would have cooled to the microwave range. The following slide is for my friends who want even more detail. Entitled "The Universe Turns Transparent," the cosmic microwave background radiation represents the moment at which the universe became transparent. Immediately after its birth, the universe was hot and dense. As it expanded, it cooled and its density dropped. Within the young universe, photons couldn't travel very far, a few inches before colliding with a nearby particle. As the matter in the universe transitioned from plasma to atomic hydrogen, 380,000 years after the Big Bang, photons could travel much farther, the width of the universe, without necessarily experiencing a collision. This moment, also called the surface of last scattering, is encoded in the cosmic microwave background radiation that we see today. The gentlemen of Robert Dickey, Jim Peebles, David Wilkinson, and Peter Roll, not pictured here, I haven't been able to find a picture of him for you, but they are all professors at Princeton, and here's that Princeton logo for you. What these scientists did was determine what the calculated value of that cosmic microwave background radiation temperature ought to be. And they calculated it should be about 2 in 735 thousandths of a Kelvin. So on the Kelvin scale, where 0 is the absolute coldest anything can be in terms of no motion, no life. And this is sometimes rounded to just 2 and 7/10 of a Kelvin. And for this class, we're just going to go ahead and say 3 Kelvin. So the Princeton scientists were able to say, okay, universe expanded, and was at a very high temperature, has cooled at a constant rate over 13.5 billion years. The photon of the last scattering should be about 3 Kelvin in temperature. Let's switch to a different team. Here we have Penzias and Wilson. Penzias and Wilson are two Bell Lab audio engineers. Bell Lab being AT&T before government declared their monopoly and broke up the company into AT&T, Bell South, so on and so forth. So they're audio engineers, and they're in the time period of working on improving communications with satellite phones. And the customers who are using satellite phones in the mid to late 60s are the very rich. And you want to keep your very rich customers happy. And these very rich customers were calling and complaining that there was this interference, this kind of static on their lines. So Penzias and Wilson were charged with essentially trying to get rid of what this noise was in the satellite conversations or phone calls. And they did everything they could to get rid of this signal that was not wanted. They even went down to the telescope itself. And this is in the background. It's a horn-shaped type of a radio telescope. And they even went down to the telescope, saw that there was a pair of pigeons that had taken residence there. And so this is Penzias and Wilson actually scrubbing the pigeon poo-poo, thinking perhaps that caused interference. And if you were to visit the Smithsonian in Washington, D.C., you would see one of the traps used by Penzias and Wilson to try and rid the telescope of its new unwanted inhabitants. Now, I'm not sure why there's this stuffed, I presume, pigeon. I don't know why the pigeon's blindfolded. I don't know why the pigeon's wearing pearls. But hey, the pigeon has their blue boots on, so life is good. Well, Penzias Wilson are trying to rid the static from the radio frequencies, and they are near Princeton, as Bell Labs headquarters is in New Jersey and Princeton is in New Jersey. And so they contact the physicists at Princeton and ask if they could give their insight and help into how to get rid of this signal. Well, the team led by Peebles and Wilkinson, they were very excited because, you've probably put it all together here, that what Penzias and Wilson had discovered was exactly what the research team at Princeton was trying to find. They had theoretically calculated the value. Now they were experimentally trying to find this background radiation out there in our cosmos. And so this is an amazing discovery in 1970, I believe it was, when the Nobel Prize was awarded for this new discovery of cosmic background radiation. So who gets the Nobel Prize? Penzias and Wilson, who are trying to get rid of that interfering static, or the Princeton team of Wilkinson et al., who calculated that value and diligently searched for that value or radiation and recognized that's what Penzias and Wilson had discovered. Well, the Nobel Prize went to Penzias and Wilson. The Nobel Prize was developed by Alfred Nobel, who was the individual who developed the concoction for TNT. He did so because he was very distraught at seeing the miners who were trying to excavate into mountains and would lose their lives with rock falling on them, and he wanted to be able to make a safe way to get into the mountainside without losing the lives of miners. And so you could implant these explosives. The miners could be far away from the mountainside and the cliffs and explode, cause the rocks to fall and be at a safe distance, and then go in and mine. When the military picked up the devastating fatal use of TNT, Nobel was just distraught. He had his invention to try and save lives, and then it quickly ended up taking more lives than it probably did to save. He was so distraught by this, the monies that were generated by the patent for TNT and other subsequent chemical patents and things that he developed, he put towards this project of the Nobel Prize. And it was twofold in purpose. One was to help with continuing efforts to produce positive gains in science studies, and also to encourage more efforts to unite the world in peace. And so you have the Nobel Peace Prize, and you have several categories in the sciences, literature, and annually awarded from the King of Sweden. So here's a Google Doodle in honor of Alfred Nobel and the Peace Prize. What is COBE and what is its significance? Well, COBE is a satellite that was launched in the 80s, and the COBE stood for the CO for cosmic, B, background, E, explorer. Cosmic Background Explorer. Essentially a satellite that was launched to, if you will, take the temperature of the background radiation. And not only take the temperature, but to see if in fact it was uniform, the same all around. So satellite is COBE, CO, Cosmic, B, Background, E, Explorer. The Cosmic Background Explorer may have been launched in the late 70s and the data processed and celebrated in the 80s. Here's the data. If you look at this top figure, as it says here, and I'll just read, the top figure shows the temperature of the microwave sky in a scale in which blue is 0 Kelvin, that absolute 0, and red is 4 Kelvin. So in between the red and the blue is your green. The blue in this image corresponds to 2 and 721 thousandths of a Kelvin, and the red is 2 and 729 thousandths of a Kelvin. You might be inclined to look at this image and think, oh, that is a vast difference in temperature. However, you have to recognize this difference in color is representing a difference of 8 thousandths of a Kelvin. 8 thousandths of a Kelvin. So that's pretty impressive and does support that the universe is at a pretty constant background radiation temperature. Zooming in even further, these fluctuations in temperatures, those hot regions shown in red, are 2/10,000ths of a Kelvin hotter than the cold regions in blue. This is getting even more detailed. And then the most composite collective image of the cosmic background radiation would be this very famous image, where you might look at it and think to yourself that, goodness gracious me, this is lots of various differences in temperature. But what we have to absolutely recognize is you're looking at very, very, very close differences. Again, it's that 2/10,000ths of a degree Kelvin temperature difference between the blues and the reds. So if you were to look at a forecast of deep space, you're going to find it's pretty consistent, minus 270 degrees Celsius. A little chilly. Wrapping up page 27, what is the significance of WMAP? WMAP? Well, this is another satellite. So in 1965, we were able to get those signals that Penzias and Wilson discovered and see that we do have fairly constant background radiation temperature and readings. In the 90s, we were able to finally composite all the data from COBE and get this very detailed image that took about a decade or so to be able to process all the data that was collected and continuously detected and compiled. And in 2003, we have, remember, about 1995, the advent of the digital camera. So that was a next phase of the COBE satellite, in essence. This is a more technologically advanced satellite. And the WMAP was able to show us an even more unified image of the cosmic background radiation. Another great thing that the WMAP was able to do often called the WMAP, was to establish that the age of the universe was 13 and 75/100 of a billion years old to about within 1%. And that 1% is 11/100 of a billion years. So here we recognize this high fine resolution image showing these 0.2 of a degree differences here. And if you notice down here, we have the Princeton logo, and this is Dave Wilkinson of the Wilkinson, Peebles, Dickey, and Roll research team. And this is the Wilkinson Microwave Anisotropy Probe, the WMAP. And so now we're able to get very close-up views of the cosmic microwave background radiation. And the finest detail that we have currently is showing the images of 15 times more sensitive in the detection of differences in Kelvin than the previous COBE results. And let's remember what the WMAP is gathering data on. Essentially, we have a satellite that is collecting the data to be able to go back and measure this uniform temperature. So the expansion of the singularity, and then that first bit of afterglow of photon energy about 380,000 years after the singularity expansion. And so this 13 3/4 of a billion years, we know the rate at which the temperature of the photons would have cooled to. So we recognize they're in the microwave band now. In 2019, the Nobel Prize was awarded for theoretical discoveries in physical cosmology, and that went to James Peebles of, the infamous Princeton team that has diligently worked on the cosmic microwave background radiation. So James Peebles right here on the left. So microkelvins, millionths of a Kelvin difference in these images here. Just absolutely outstanding data over the last few decades. About 1% of the static on your television that you really don't see these days with our 4K and ultra high definition televisions is the static from the cosmic microwave background radiation. So if you're in a car with a radio, then take some time and untune your radio. That means don't land on a station, but put it on manual search and just listen to some static. And 1% of that static heralds from the Big Bang time. So amazing to be able to really be in tune with the cosmos. Great evidence with the cosmic microwave background radiation for Big Bang nucleosynthesis.